Okay, let's get started. So it says lesson 22. That should say 26, by the way. So just caught that right when we started this, so that's fine. All right, so lesson 26 will deal with function decomposition. So we're done with trig. Last topic I want to talk about is function decomposition. So just to recap really quick, you may remember composition of functions, right? And that's whenever you had something that looked like this. F circle g of x, which just meant f, the function f, with g of x plugged inside, right? So that was composition, where you took one function, you plugged it inside of another one. Okay, well, what we're going to do now is actually, given a function that may be sort of complicated, we're going to decompose it into the separate functions from the beginning. So you can have the two functions separated. Okay, and so that's what we're going to be doing. So instead of using f and g, what we'll use, just to make it easier, if we have a function and we want to decompose it, let me separate these two, we'll separate it as u of v of x. Okay, so we'll use u and v. Okay, and that's just kind of standard notation that you'll see, especially in calculus. Okay, all right, so let's go on to our first example. Let's decompose this sort of complicated function here into two components. And again, just to remind you, off to the side here, I'll write it out in red. We want to decompose it by finding u and v such that u of v of x gives me this right here. Okay, so that's what we're shooting for. All right. So there's actually several options. Maybe you're looking at it, but what you're looking for is a function that's embedded within a bigger function. Okay, and so maybe you see it, right? Maybe you see this 4 plus x squared as its own function. It's usually easier to identify v first. So I would say maybe v of x is 4 plus x squared. Okay, well then that would make u of x 4 over 3 minus the square root of, I just took out that 4 plus x squared. So if this is its own function, that part right there is the variable that changes. That part would be x. And so here would be one scenario. I don't like my box. I'm gonna draw another one. Okay. So that's one scenario there. And you could see if you composed it, if you took this x out and replaced it with v, that would be the same thing as the original. Okay, so that's one option. Another option you may see, what if this whole square root of 4 plus x squared were its own function? What if that were v? Well, the functions would look very similar. U of x this time would be whatever I just boxed in would turn into an x. So it'd be 4 over 3 minus x. All right, there's another option. Okay, I see several more. I'll do one more option though, one more that I see. We'll say v of x. Let me erase the green here. Is this x squared? Okay, so I'll put the box around x squared. So that means u of x would have to be 4 over 3 minus the square root of 4 plus x, right? If you composed that, or those two functions together, you would get the original. Okay, so that's three options. There are more. So that's one of the fun things about this, is that there's so many options that everyone can have a different answer. Okay, here we're asked to write the function as a sum. Okay, this is sort of a product, right? This is 2x plus 1 times itself 3 times, right? 2x plus 1 times 2x plus 1 times 2x plus 1. So I want to write this as a sum. And the way you do that, of course, is to actually multiply it out. So let's go ahead and do that. I'm going to go ahead and write f of x equals, and then leave myself some space. 2x times 2x would be 4x squared. 2x times 1 would be 2x. 1 times 2x would be 2x. 1 times 1 would be 1. Okay, and then that's all just going to be its own thing. I'm going to leave the last 2x plus 1 alone for now. I'll deal with that later. Okay, so if I combine my like terms, I'd have 4x squared plus 4x plus 1 times 2x plus 1. Now let's do this again. Distribute 4x squared times 2x would be 8x cubed. 4x squared times 1 is 4x squared. 4x times 2x is 8x squared. 4x times 1 is 4x. 1 times 2x is 2x. 1 times 1 is 1. Okay, combine my like terms. And I'll get the function written out as a sum. So 8x cubed, I have 2x squared. So 8x squared and 4x squared is 12x squared. 4x plus 2x is 6x, and then 1 plus 1. So there we go. So notice we just represented the function another way, right? It's the same thing, we just multiplied it out. Now it's a sum because it's separate terms added together as opposed to terms multiplied together. Okay, write the function as a product and then decompose. Okay, so let's pay attention to the order here. Write it as a product. We'll do that first, which just means to factor it, right? We talked about that before. Writing something as a product essentially just means we're factoring it. We're breaking it up into multiplication. So something times something, something times something. You might recognize these two as perfect squares. If you ever see that, you want to try first 4x, 4x, 5 and 5, because those will probably work. Also notice that they have to multiply together, be a positive. So these have to either both be positive or both be negative. But since they have to add up to be a negative 40 or add it to be negative, I'll put them as both negative. Okay, so that's my guess. I don't know if that's right yet. I'll check it. Negative 5 times 4x is negative 20x. 4x times negative 5 is negative 20x. If I add those two together, I get negative 40x, which is the middle term. Okay, so I do know that this is correct. Okay, so I can actually simplify that a little bit. It's 4x minus 5 squared, because there are two of them. Okay, and so now we want to decompose this one. Okay. So what would, let me go ahead and write this in blue, decompose. Okay, well, the inside function could be this 4x minus 5. Which means, okay, the box is drawn here. That becomes the x. We have x squared. So u of x would be x squared. Again, just to remind you, that means that if I were to compose u of v of x, I would get f of x. Okay, so the last type of problem that I want to go over deals with writing a rational function as a sum, okay? And so what I mean by that is that if I were to go and let's say factor the denominator here, and this one factors to be x plus 7 and x minus 2. I want to rewrite this function in such a way that it's something over x plus 7 plus something over x minus 2. But I don't know what those somethings are, so I'll just call them A and B. So the goal is to find A and B, okay? Well, let's think about how you would add these together if you were adding them together. You might remember the process here. You would multiply this one by this one's denominator. So that would be x minus 2, x minus 2. And you would multiply this one by this one's denominator, at least the original denominator of x plus 7. Okay, and so if I did that, let's compare these two fractions with this one here. Notice the numerator is 4. The numerator is 4. So these are the same denominator, so I can imagine that this is all one fraction, right? That's added together. The numerators are added together. And so ax minus 2 plus bx plus 7 equals 4. The two numerators added together should equal this numerator here. Oops. Okay, and so from there, you can set up a system of equations, which is usually how you learn how to do this, but I want to show you a trick, okay? A little shortcut. Not thinking about the original function, but just thinking about this equation right here. I have two scenarios, okay, that I want to play out. What happens if x equals 2? Well, imagine that for a second. If x was 2, then I'd have 2 minus 2 here, which would be 0, a times 0, plus 2 plus 7 is 9. In other words, I'd be just solving the equation 9b equals 4. We all know how to do that, right? That would give us b equals 4 over 9. I found b. To find a, I will just pretend like x is negative 7. If x is negative 7, then, all right, negative 7 right here would give me negative 7 minus 2, which is negative 9. Negative 7 right here would give me 0. So b times 0, those equal 4. In other words, negative 9a equals 4. Or, I don't know why I switched to a capital A there. Go back to lowercase. A equals negative 4 over 9. So I found my coefficients. So now I can actually just go and plug them in for a and b, ignoring all the blue writing there, right? My function f of x is equal to negative 4 over 9 with x plus 7 in the denominator. Notice how I put the two denominators together, right? There was already a denominator. A had a denominator, so they can actually just go together as a product. Plus, I'm gonna do the same thing with b, 4 over 9, x minus 2. All right, these two are the same function. You look at the graphs and tell that. Here's the graph of the original function, f of x. Here's the graph of the function we just found. You'll notice they're the same exact thing. Okay, so now that we know that little trick, let's do a little bit more complicated problem here. So I want to rewrite this and factor the denominator, and I'll factor it quickly. I'm gonna go 5x, 2x to give me my 10x squared. And I'll do 1 and 3 to give me a 3. I need a positive and a negative. So I'll put the positive here and the negative there, because in my mind, I thought those together is negative 2. Those together is a positive 15. Add those together and I get positive 13. Just practice a lot and it gets easier, right? Okay, and then you can picture the new function having a fraction 5x minus 1 plus b over 2x plus 3. And without actually writing it all the way out, remember you multiply this denominator there. We're only going to look at the numerator, so I don't have to write the whole thing out. And this denominator goes there. And when you add the two numerators together, the new numerators, right? Remember the denominators here, it's just going to be 5x minus 1 and 2x plus 3. Right? But I don't actually want to write all that out, too much writing. When I multiply those or add those together, they'll equal 8 minus 3x. Okay, so let's use that trick from before. I'm going to find the fraction that makes this one 0. Now that might be a little bit of extra work, okay, to make that equal 0. So I'll just do 2x plus 3 equals 0. And then solve that really quickly to decide what x I want to plug in. Negative 3 over 2. So if x is equal to negative 3 over 2, we know that this one's going to be 0. This one will be different, right? So that'll be negative 3 over 2 minus 1 equals 8 minus 3 times negative 3 over 2. All right, so it's ugly to deal with the fractions, but it's still easier than dealing with the system of equations that come up. So b is equal to negative 15 over 2 minus 1, or b times negative 15 over 2 minus 1 is equal to 8 plus 9 over 2. And then I'll quickly do these two. So that's going to be negative 17 over 2 equals 25 over 2. To get rid of the negative 17 over 2, I'll multiply both sides by its reciprocal. That's not the reciprocal. B is equal to negative 25 over 17. Okay, so plugging in negative 3 over 2 for x gives me b having to be negative 25 over 17. Okay, let's decide what to plug in for x for the second case. Add 1 to both sides, divide by 5. I get 1/5. So if x is 1/5, then, well, this one's going to equal 0. So we're going to ignore b. 2x plus 3 will become 2 times 1/5 plus 3 equals 8 minus 3 times 1/5. So a times 2/5 plus 3 equals 8 minus 3/5. Again, I'll just do that quickly. So 3 is 15 over 5 plus 2 is 17 over 5. 8 is 40 over 5 minus 3 over 5 is 37 over 5. Multiply both sides by the reciprocal of 17 over 5. That'll cancel out my fraction on the left and leave me with 37 over 17. 37 over 17. Okay, so that would be the coefficients that I needed. So I can go back now and finally plug those in. Let's see where I'm gonna plug them in. Let's just do it right here. So the first one was A was 37 over 17. And B was negative 25 over 17. So we'll change that plus to a minus. And there we have it. Good thing there's a shortcut, right? Because these get really ugly if you don't have the shortcut. They're ugly enough with the shortcut. All right, anyway, I'll stop recording.